In today's video, we'll be talking about electromagnetic induction. After watching this video, you should be able to explain how Faraday's experiment proves that a current can be induced in a wire using a magnet, and then we're going to introduce a new formula called the EMF formula. So let's get right to it. How did Faraday's experiment work? Well, basically Michael Faraday, he came up with this idea that if you take a galvanometer, which is this little instrument down here, it measures current, and you connect a wire to it, then have that wire wrap around some metal rod and then connect back to the galvanometer again. And if you take a magnet and put it in between this metal rod and take that metal rod and move it up and down, or make the magnet move up and down, this galvanometer will show actually a current, that a current has been created either by the magnet moving or the rod moving. It just has to be within that magnetic field. And making a current through this way is called electromagnetic induction. And this is actually how electric generators work. If your power ever goes out, and if you do have a generator at home, basically there's some magnet with some coiled wires that are moving relative to one another, and thus that generates a current and can help power your home. The electromotive force, the EMF, is actually kind of inappropriately named. It was named at a time when people really didn't understand what was going on, and so they used the word force. And it's not really a force, but instead it's a voltage. It's kind of this unit of energy per charge. So EMF you can think of as actually a voltage, and it's not a force. So we're not actually introducing a new force today. It's just one of these things that is kind of stuck around and no one changes it. I don't really know why it is this way, but lo and behold, they call it an EMF, or the electromotive force, but basically the same thing as a voltage. So you may say to yourself, what actually gave that potential difference, or that voltage, if you will, in Faraday's experiment? Basically, when that wire moves through a magnetic field, a force is exerted on the charges in that wire, and it causes those charges to move. To make something move, basically work is done on the charges, and so thus their potential energy is increased. Now we're going to get into all the nitty-gritties of it, but basically just kind of keep this idea in mind that if you get charge moving, that's a current, and to make that current happen, there had to be some sort of work done on those charges to get them moving, and thus you have this energy that can be used to, turn on a light bulb, power a microwave, what have you. Okay, so it all kind of ties in with the second right-hand rule, where basically if you have charged particles moving in a magnetic field, they are getting a push, a force, they're experiencing a force, and thus they're getting a push, and so work can be done. There are a few requirements to induce a current, nothing probably out of this world crazy. Basically, you need a conductor that moves through a magnetic field, or the magnetic field can be moving relative to the conductor, but movement has to occur. They can't just sit there stationary. And the second thing is you need a wire that can conduct electricity. So that's probably pretty obvious, but if you try to wire your house with styrofoam or something, I wish you luck. You probably will not have much of a current moving with something that's an insulator. The formula for calculating EMF is this guy right here. EMF, which is a voltage, is equal to B, which is the magnetic field measured in Teslas, times L, which is the length of wire in meters, times V, which is the velocity of the wire. How fast is it moving perpendicular to the magnetic field? Remember, we only get things happening if things are moving perpendicular to one another. So if they're moving parallel, you don't actually calculate, or you don't get an EMF. And so that's what that sine theta piece is basically you want to make sure you're moving perpendicular to it so that you actually do calculate an EMF. Because remember, the sine of 0 degrees is 0. The sine of 90 is 1. In some college physics courses, you probably will actually have different angles other than 0 and 90, but in our class, we'll probably only have problems of 0 and 90 degrees, unless it's like an extra credit question or something like that. The big thing to kind of keep in mind is the units of EMF is not the Newton, because it's not a force. Instead, it's actually the volt. And if you remember, a volt is how many joules of energy you have per coulomb of charge. So that's the units of EMF. Let's do a little example problem. What can you expect to see, say like on homework or a test or something like that? It says a straight wire, 0.2 meters long, moves at a constant speed of 7 meters per second perpendicular to a magnetic field of strength 8 times 10 to the negative second Teslas. What is the induced EMF in the wire? All right, well, let's see what happens here. Remember, our formula is EMF equals E times L times V times the sine of theta. All right, I'm sorry, my handwriting's so poor, but let's see here. What do we know? Well, the magnetic field is 8 times 10 to the negative second Teslas. So that's really 0.08. I'm going to take it out of scientific notation. 0.08 times the length of the wire, which is 0.2 meters long, times the speed that the wire is moving. It's moving at a speed of 7 meters per second, times the sine of the angle between the wire and the magnetic field. Well, in this case, it says it's perpendicular to, so that's an angle of 90 degrees. So we're taking the sine of 90, which is actually 1, if you recognize that. But if not, just throw it in your calculator. It's not a huge deal. If you throw these numbers through your calculator, you get an EMF of 0.112 volts. And that would be the answer. Okay. Now, what's kind of cool is, or at least I think is cool, you may not, is we can now start to incorporate this with some of the problems we saw in circuitry. Okay, so let's pretend this is your generator, and you connect a wire to this generator, and if the wire is part of a circuit that has a resistance of 0.5 ohms, let's say you put like a little small light bulb in it or something like that, 0.5 ohms of resistance, what is the current through the wire? Okay, what is the current through the wire? Well, to solve this, you have to kind of think back to the time when we were dealing with circuits. You have to use Ohm's law, and Ohm's law is basically I equals V over R. Now, I just arranged it this way so that we have current by itself. You can manipulate it however your heart desires. So we're trying to find the current, which is I, and we just calculated the voltage. The voltage is 0.112 volts, and the resistance is 0.5 ohms. Right, so I just did V over R. And if you do that math problem, I get a current of 0.224 amps. Okay, so you can kind of see how this all can tie together with other chapters that we've talked about previously in the course. All right, so that's an example problem, something you could possibly see on, say, homework. So this generator, the electric generator, was invented by Michael Faraday, the guy who did this experiment. And basically what a generator does is it converts mechanical energy into electrical energy. And basically if you connect that generator to a closed circuit, you can create an electric circuit. And some of you may have seen like handheld generators. I know at hardware stores you can buy flashlights that if you crank it, the flashlight, there's like a little handle to crank or whatever, you can turn it on and then you've got light for a period of time. Your body is actually the mechanical energy that's being converted into electrical energy to then provide light. And this is just a real simple generator. Basically, there's a little motor attached here, and these are coils of wire, and they're going to spin in this magnetic field between this north and south pole of two different magnets. And since this is spinning, in between these two magnets, you're going to get a current induced in those wires, and thus you could convert that electrical energy into something else that's useful for yourself. All right. That actually takes care of this video. I will see you guys next time.